Now, of course, we can go back and we can drop this half and CC and understand for ourselves that we are going to use the complex amplitude for the electric field, although it is a real quantity, right. And then the square root of IT is the real amplitude of the pulse, right. So, we of course, there is an ambiguity in taking square root. So, we will stick to the positive square root uniformly, okay. It does not hurt us, it is after all a factor of additional phase of pi between the two, but we will stick to the positive value of the square root. The other thing that I should have sort of done in the previous view graph, which is important, is look at the time axis. It is a bit strange if you observe the time axis, it has negative values, right. It has it has negative. We know that physically, I mean, there is no, unless you ascribe some special meaning to it, having negative time means nothing, right. Unless we admit the meaning to it, that there is a past and a future or whatever, that is a physiological notion of time. But here the point being that here the time axis also owes some respect and explanation. It is the following: what this form of keeping the time axis means is again the following, that this is t, this is square root of I t. So, if I have a pulse in time, sorry, let us say, should I draw it that way? Yeah, if you have a clock, if we have indeed a clock somewhere, at any instant, if I take a snapshot of the electric field amplitude, it is centered when the clock has t1, the description of the pulse is like this in time, right. Now, at time on the clock t is equal to t2, the pulse has moved forward. At t is equal to t3, the pulse has moved further forward. It, of course, it is a propagating wave in a lossless homogeneous isotropic medium. It will retain its shape, although my artistic skills are not good enough to sketch even just 3 Gaussian shaped functions identically, but modulo that these are identical. So, the pulse is merely propagated forward. So, therefore, there is absolutely no point in keeping track of T1, T2, T3 and so on. I realize I have also made an error over here. The first time is just T sub 1, right. So, this is T2, this is T3, that clock has ticked. So, we are merely keeping track of a sort of trivial ticking clock by subscribing to some notion of absolute time, which anyway relativity tells us is fairly meaningless. So, therefore, what we do in these descriptions is do the following: we simply decide that we will run along with the pulse and live in a boosted frame. So, we perform a Lorentz transformation. If you are a physics person or a physics specialist, if you wish, and you run along with the pulse, and you have what we would describe the pulse in what we can call a co-moving frame, a frame of reference which essentially moves with a velocity v. I will subscript it with g, okay, along with the center of the pulse. In that frame of reference, if I describe the pulse, I need a 0 for my time axis. Yes. Now, this pulse was centered at T1, T2, T3, the time on the clock. So, I reference all other times across the pulse with respect to T1, T2, T3. If this pulse has a Gaussian amplitude, indeed the amplitude does not die down to 0 even for large values of t per definition. Okay. So, I have to keep track of the entire time axis even to describe a single pulse, okay, which can be a numerical nightmare unless treated well enough, right. You can imagine that, but then there are times before T1, there are times after T1 or T2 as the case may be. Therefore, I plot in a plot like this the differential time away from a specific reference point in the pulse, which we conveniently reference to the maximum of the pulse envelope and stick to it consistently. Okay. We must stick to that. Consistently, that is the key to it. Alright. So, that defines the 0 of time, and hence you have negative and positive values for the time deviating away from it. Alright. So, we have a real amplitude and we have real light pulses and we have a formal description of the same, right. So, now in this form of writing the electric field here, we have removed two aspects. One is the half and Cc, the other is the omega naught t, which is the carrier frequency. All right. In which case this removes the rapidly varying part, we only have, and we have a complex quantity. After all, the carrier frequency per definition here is a single number. So, track it separately, that is what we are saying. Write this in a more compact form and we still have a complete description of the pulse. In fact, since the carrier frequency is a constant number, right, what matters is the spread of frequencies around it and amplitude. So, we can even set that to 0 as we will see and we will be doing shortly. Okay. So, but let us come to at least define one pulse, having said that this lecture is about light pulses. Let us complete the description of a pulse by choosing our favorite Gaussian function and describe a pulse which is Gaussian in amplitude. Okay. So, it is a good approximation that we take these ultra short or femtosecond light pulses. I have not carefully enough defined the adjective ultra short, but you have a notion. Here we have considered pulses where the time period of oscillation is of the order of some femtoseconds. It was say maybe 2 or 3 here, and the pulse rose up from from nearly 0 amplitude or let us say from few percent of its maximum amplitude to its maximum in about 15 femtoseconds and drop down in the next 15 femtoseconds, or even shorter here from its maximum value to a few percent of its maximum. So, such a pulse is in a way as short as it can get. So, we call it ultra short. But not all light pulses need to be ultra short or subscribe to that definition, they would still be perfectly honorable light pulses to deal with, but this is a good notion to carry forward in this course. So, but then the amplitude itself was, we considered a very general amplitude, no neat functions, but we can use a Gaussian function to describe ultra short pulses formally. It is a matter of say convenience, you can say mathematical convenience. And the Gaussian function has its specific mathematical descriptions where it has the amplitude or the envelope function of the pulse E of t is exponent of t the time variable divided by the variable that connects to the width of the Gaussian, which is tau half width at 1 over e point. If you use this tau, then you get the simplest expression for the Gaussian function in its mathematical description. That is, if I take a Gaussian and write it down as E of t is E naught e to the minus t by t squared by some tau squared. This corresponds in the simplest form, this tau something is the tau of the half width at 1 over e point. Okay. Now, keeping this definition consistent, the other factors that are of importance over here, which is tau full width at half max, our favorite measure for widths in this course, which we have used already once, will turn out to be, as in this case, it is tau half width at 1 over e divided by the square root of 2 log 2. Okay. Now, oftentimes we simply write a Gaussian description of the pulse to be e to the minus t squared by tau squared, in which case this tau relates to tau FWHM, which is, as I said, the popular measure, through this factor 2 log 2, which translates to the square root of 1.38 or approximately 1.4. So, half width at 1 over e is also the half width at half maximum roughly. These are all notions that we must use a bit carefully, but oftentimes we do not do. And FWHM is the full width at half maximum. So, now since electric field is the and intensity are related through the absolute value squared, then the intensity function itself also has its own description. It is again Gaussian if I start from the fundamental electric field, but then if I look at for the same electric field, I convert it to intensity, right, then the full width at half max T FWHM, the width of the Gaussian function in electric field and in intensity are different by a factor of square root of 2. Okay. It's just a consequence of the math, because a factor of 2 got multiplied here in squaring the electric field over to get the intensity. So, please note this, again something which we must pay careful attention to, especially when you are computing few quantities. In reality, it kind of looks like this. It is indeed for the same pulse, the intensity envelope is a tad bit narrower than the amplitude envelope. Okay. In this pulse, the way I have sketched it here, note that the carrier frequency remains constant throughout, right, which corresponds to the function phi of t being constant, and we can set that unambiguously to a 0, right. So, that is the intensity versus intensity, amplitude and time on the same plot, and this pulse is also ultra short, right. The way the notion of ultra shortness is sort of built into this pulse. We have one period to be so much, and the intensity falls from maximum to nearly nothing after about 1, 2, 3, 4, 4 to 5 periods. It is actually a really short pulse, the way that we have described it, really from a practitioner's perspective. So, it is more than just an ultra short pulse. It has only few carrier cycles in a region of time where the envelope has appreciable intensity or amplitude. So, it is pushing it to the limit that it can be such a pulse in itself. Okay. So, we will in the next discussion, which we will have tomorrow and day after, one of these lectures we will make it a tutorial. So, we will see about that soon. We will discuss about the intensity, the phase and so on, based on the formal description that we have arrived at in this class. Okay. So, the lecture is formally closed. If you so wish, we can still further discuss anything that sticks in your mind while the iron is still hot. No.
So, my earlier question was actually about.
I did not answer it, is it? Fair enough. By the way, online audience, you are free to please raise your hand, put up a chat comment or something, so we do not leave you out. So, please please feel free, we have some time. As long as my colleague here can keep things up, I will be happy to have a discussion. Online audience. Thank you. Go ahead. Recording is done, no problem. Yes, Amna.
If I understand correctly, the pulse nature of this comes from the IFT.
Very yeah.
But what does the time dependence of phase has to do with it? Why did you?
It's not, everything is not obvious as always. So, it will, I want the most general description of the pulse. Okay. So, if I may indulge in some analogies which may or may not always be whatever, it is like us, each of us is, having the same chromosomal content or whatever, but the point is it is a matter of description. There is a wide range of descriptions that we need to admit. So, statistically speaking, yeah, we are beings with these characteristics, mammals, that, and so broadly we would leave it at only that if we had just a constant carrier frequency, but there are all kinds of pulses can be admitted, right. So, for example, this in the case of this pulse, you see that the frequency is increasing in time. Well, we would not possibly be able to speak if we could not do this with our vocal instruments. The carrier frequency as we speak changes in time, as you sing changes in time, as you say anything it changes in time. Even in the most easiest of languages, a chirp of a bird or a whistle, that is frequency changing in time, right. So, this is the more general description. It is mathematically and pedagogically convenient to start with one carrier frequency and run it. That is why remember that a wave with a single carrier frequency is infinite in time. With exactly one carrier frequency is an infinite wave. Even the universe has a finite age, or as we know it, from now to the so called singularity or whatever, it is a finite duration of time. So, therefore, okay, but that of course means that we need to admit some bandwidth which comes about from you are introducing an envelope in time, right. So, everything on and off time need to be taken into account. So, there you are going away from monochromaticity, strict monochromaticity, but you should also view it in another way. Any source, okay, any real world source has nothing infinite attached to it. It is physically, it is unphysical to have any infinity, right. So, what this simply means is that any real world source can sustain an oscillating wave of any kind only over a finite duration of time. If we had this, the previous wave even in the case of a very monochromatic wave, could I mean you have to admit the fact that the phase can get broken, otherwise you have infinite coherence, right. So, that is one reason for why you have this. Likewise, the next step in this description is to admit it need not have a Gaussian envelope, but a chirp wave. Say it even if you do not like it, if there is a Doppler shift between the source and anything that is receiving the wave, that is enough to cause a chirp, at least a perceived chirp if you wish. There will be a frame of reference where this happens, correct. So, all this essentially means that we need to have a description where we essentially go away from constant frequency to something else. But yes, that is how we are viewing it. It is a deviation from constant central frequency to something else. That is why we are writing it as omega naught t minus a phi. Soon we will throw it away also and say it is a capital phi of t and capital phi of omega, a temporal phase, and if I have a phase function which is temporal phase phi of t, whether it has physical meaning or not, it is perfectly legitimate to Fourier transform it. So, I will, that is all. So, then there is a concept, but this is what is this quantity? It is a phase, right. So, is this is also phase. Fourier transform does not change the dimension of your physical quantity, it just changes the variable, right. So, phase and a phase. So, these we will see, or that is the whole goal of the first discussion, that these are equivalent descriptions, time domain and frequency domain. So, temporal phase and spectral phase will both play a role. If now your spectral phase is constant in time, no, is linear in time. So, therefore, we should actually not, spectral phase can be, no, sorry, let me not go there. The spectral phase, yeah, sorry, yeah, can the spectral phase be spectral phase, no, that is not wrong, that is not right, let me not go there, I should think it through more carefully. But all I am saying is that you would end up having two phase functions. Let us keep it there for the moment. The rest I do have more details in the further description of the course.
You are saying if I have a temporal phase which is constant, which is the same, which is like phi, just like how DC has
then the wave will not propagate, of course. If its phi of t is constant, there is no propagating wave, because why does phi of t not have, phi of t being constant mean that there is no propagating wave?
because d by dt of phi of t, then
So, frequency is 0, but why can't 0 frequency propagate?
wave.
It is actually a simple thing which I also got stumped by this, thinking about this, or when I did not think about it, rather, and decided to think about it. Why can't we talk about DC as something propagating, or why do not we consider that as part of the description of a propagating wave? Oh, again it is question of infinities. The period for the wave to repeat itself is again infinite, so it is unphysical. So, a DC field is DC, it does not propagate, it is local. So, also for wavelength, right. So, this is Fourier transform wise equivalent to, if I were to have a DC field, the spectral content of the pulse, if I take omega, the central frequency of the pulse, and create the broadest bandwidth, go from omega is equal to something to 0, if I admit the entire bandwidth, it would leave me with a pulse and time which is one cycle. I would further need to go into some unphysical notion of negative frequencies to make this a flat thing and propagate, which is entirely unphysical. All right.